So welcome back. That's part 2 of our second lecture. So let's start opening the black box of ridge, looking at the mathematics behind ridge regression. So basically what I'm going to talk about now is the solution of the ridge optimization problem. We're going to look at the moments of the ridge estimator in low dimensions, and also consistency and asymptotic normality of ridge when p less than t, and the relation between ridge and principal components. Okay, some references for ridge, these very nice lecture notes, as I have already mentioned to you. You can download from arXiv, section 3.4.1 from Hasty, Tibshuran, and Friedman book. And if you want to learn more about theoretical properties of ridge, especially in ultra-high dimensions, this very recent paper by Dobribin and Wager in Annals of Statistics. Okay? Although the main topic of the lectures is not principal components, but we are going to mention principal components here. So if you want to refresh on that, here you have some references. Okay? So ridge regression, you all know, we have just seen that. That's the problem of ridge regression, the square penalties that we are going to introduce in the minimization of the mean squared error. Okay, this penalization will have closed form solution. So beta hat ridge is given by x prime x plus lambda I inverse x prime y. Okay, and drawbacks is that in general the estimator won't be consistent unless in specific situations, and I'm going to show you which situations are these. And it's not a tool for variable selection, but as I have already mentioned in several occasions, it will be quite good for prediction. Okay? So let's look at this plot here. What I did, I simulated data from a regression model with 10 covariates, 10 regressors, okay? Number of observations equal to 10. And both x and mu's, the covariates and the errors, come jointly from a normal zero with identity covariance. And what I'm showing here are the estimates for the ridge coefficients, the beta coefficients, as a function of the penalty term. So as I increase the penalty term, what happens to the ridge estimates, okay, for the 10 variables? So what we see is that, of course, when the penalty is 0, we have unpenalized estimator. They are all far away from 0. As we increase the penalty term, we are shrinking the coefficients towards to 0. And it's a continuous path, you see? It's a continuous function, very smooth function of lambda. Okay? So now let's zoom in here to see what's going on in the limit here. You see the coefficients are pretty small, but they are not exactly to 0. And I am increasing the value of lambda, but they are still far from 0. Okay, so we are not really sending it exactly towards 0 as I mentioned to you in our meeting last week. Okay? But the important thing is that the ridge path is continuous, it's smooth, and converges to 0, but it will be equal to 0, the estimates only in the limit when lambda diverges to infinity. Okay? This is another situation where we have t equal to 5 and p equal to 10. So we have more covariates than observations. So you see still the path is continuous, it's smooth, and it's going to 0. But then is it exactly equal to 0? Let's take a zoom. It can be quite close, but not exactly. So that's the point. It's not exactly equal to 0. Even with very high amount of penalty, it's not exactly equal to 0. Okay? So what ridge is doing let's look at the case where t less than t. Because why is that? Because beta will be well defined and we can compare with the OLS. Okay, so call x prime x r just for convenience. Okay, then we have our beta reach x prime x plus lambda I inverse x prime y. Let's replace x prime x by r here, and here what I'm going to do, I'm going to multiply by r inverse, so this is equal to identity, right? So I'm doing nothing here just for convenience. Okay, now what I'm going to do, I'm going to take this young man here, put it here. Okay, sorry, what I'm going to do is like take this guy here, put it in evidence, so be r identity plus lambda r inverse, okay, inverse of everything. Keep this gentleman here. This r minus 1, let's go back to the original notation, x prime x minus 1. Okay? So the only thing I did here is to put this gentleman in evidence, okay, in front of the parentheses. Now, what we have, okay, but then I can take it out here. So I can leave identity plus lambda r minus 1, and this gentleman can come out sorry, of the inverse, and then we have inverse of r, but what is this quantity here? If p less than t is exactly beta hat OLS, for assuming that beta OLS exists, so that this inverse exists, right? All right, so, but what's this term here? Oh, this is identity. So the beta reach is the beta OLS. Again, this is important, because then this is well defined. This is the beta OLS multiplied but by something here. And remember, this is positive, right? Because this is our x prime x. So, of course, if this is a diagonal matrix, we are going to shrink all the coefficients towards 0. Of course, if this is not diagonal, things are not crystal clear like that. But it's really similar to the James-Stein estimator. We have the unpenalized estimator that's multiplied by a term. Okay, that's the shrinkage term. So let's take expectations. So what's the condition expectation of the beta reach on x? Is the expectation of the identity lambda r minus 1 inverse of everything beta OLS, beta hat OLS given x. Okay? Take the expectation again with respect to the distribution of x, the law of iterated expectations will give us this term. So the expected value of beta reach is different from beta. Okay? So the reach is a biased estimator. Okay? It attenuates the OLS estimator. Okay? So it be only unbiased when this term here vanishes. Okay? And this whole thing here becomes identity. Otherwise, the estimator is biased for a fixed value of lambda in low dimensions. Okay? We cannot do this in high dimensions because this is not well defined. So it's much more complicated to try to derive the properties of reach in high dimensions. These things, again, will become clear when we look to the true high dimensional case when we talk about the lasso next week. Okay? Okay, so what's that's the expected value, but what's the variance of the reach when p is less than t? So let's define that the covariance matrix of the errors is sigma squared times an identity, and let's call that term that appears here in front of beta, let's call this term W lambda. Okay? So the beta hat reach is W beta hat OLS. So the variance, the conditional variance of beta reach on X is sigma square W x prime x minus 1 W. Why is that? Because we can write this in terms of the variance of the beta hat OLS. And the variance of beta hat OLS given X is sigma square x prime x minus 1. Okay? So now we have an estimator with this term in front of it. So that's the expression of the variance of the reach. Okay? So that's exactly what I wrote now on your screens. So as a consequence, the variance of the OLS, okay, will dominate the variance of the reach. So what we are seeing here that we introduce a bias in the reach, but we can reduce the variance, such that we can have an estimator with a lower MSE. The bias variance trade-off kicking in. Okay? And the mean squared error, if we open it and compare the beta hat with beta, we can easily show that this term here will be sigma square, the trace of that matrix here, this will be the variance, plus the square bias. That's exactly what we have derived in the previous slide, right? So that's the square of the estimation of the previous slide. So this is the variance, and this is the square bias. Okay? So the idea is that we can, for a value of lambda, we can have a bias increasing from 0 that we have in the OLS, such that the variance will decrease in a way that the mean squared error will decrease. Okay? We can discuss more about this during our live meeting on Friday. Okay? So now, second question, so now we know what's the expected value and the variance of the beta hat reach, but then we can ask, okay, but why reach works in large dimensions? Because if we go back here, what we are just doing with the reach is like taking the original OLS formula and adding something to the diagonal of this matrix. So the problem with OLS when P is less than T is the problem that the rank of x prime x is lower than P. So x prime x minus 1 does not exist. right? But now we are adding something to the diagonal, and we make, and magic happens. Why? Well, that's what we are going to see here. So take the reach. So again, what's the reach estimator? Let me write here again. So it's y t minus beta xt square t equal to 1 to t plus what? Plus lambda 1 to p beta I, that's j, beta j square. Okay? All fine, right? But do you agree that we can take this lambda and move here such that forget about this and write this way? J equal to 1 to p square root lambda beta j square. Okay? Same thing, right? Now let's do the following. I can include a 0 and a minus term here, because the square of this thing here is exactly this square, that's exactly the sum that we had before. Okay? So compare these two summations here. The first one, we have something here, a term, minus, okay, another term, multiplying beta, everything squared. Look at here, we have a sum of something, a term, minus another term times beta. Okay, it's beta j, but we can make this vector, this thing here, depending on j. Right? So we are adding what? More observations. So this is like having p extra observations. So it's like writing the augmented data set in the following way. Let's define an x lambda where the first t observations are exactly our x. Okay, no problem. But the remaining p observations, here we have like t rows, and here we are going to have like p rows. We are going to have square root lambda over the diagonal, zeros or the y's of our p variables. Because you see, here is like having a square root lambda for variable j, for observation t plus j, and 0 all over. So that's exactly what we're having here, and defines the capital Y lambda, our first t observations, it's like t observations, and here our p observations, a bunch of zeros. These zeros that we have here. Okay? So it's like we doing reach is like increasing the data set by p observations. So instead of having t observation, now we have like t plus p. Okay? So we got guarantee that in this augmented data set, we have more observations and variables. Because we have like p variable, we have like p parameters to estimate. But now we have t plus p observations. So we have t more observations. Okay? Because it's t plus p. That's the trick. So what's beta reach is an OLS on the augmented data set. So it's OLS on the augmented data set. That's what reach is doing. So that's the reach estimator. If you open this estimator, you get the usual definition of the reach estimator. So bingo. That's why reach works. We augmenting the data set. So we create artificially a large data set. Okay? And of course, x lambda prime x lambda will not be singular, even if x prime x is singular. Okay? So that's the trick behind reach. Next result, is reach consistent? Okay, let's see if reach is consistent in situations where lambda diverges, but lambda divided by t goes to 0, so t diverges faster than lambda, and p less than t. So we are back to low dimension. Okay, the previous slides were general. Now we are back to low dimension. So what we are going to do? Now we are going to make explicitly the dependence on lambda on t, on the sample size. Okay? So now we are making sure to have it lambda t. So that's the reach estimator. So what we are going to do? Replace y by the definition of y. Remember that y is x prime b plus u. That's exactly what we have here. That's y. Then multiply it by x prime x beta, x prime u. Now, sum and subtraction trick. Sum lambda, subtract lambda, lambda beta. So this is an identity matrix and this is beta. Okay, nothing changed. Now what we are going to do? Put this beta in evidence outside of a parenthesis. Okay. Keep the rest as it is. Now what we have here, this term multiplies that term here, okay, this one here with this one here. So you see this in inverse, no inverse here, so we get beta here. Then this term here times this term here, that's what we have here. And finally, this term here times this last term here, that's what we have here. Okay? So what we have here is beta, beta here. Now I'm going to take this divide and multiply by t. So inside the parentheses, because we have the inverse here, it will be x prime x divided by t, lambda t divided by t, lambda t divided by t beta, plus lambda prime x divided by t plus lambda t divided by t identity x prime u divided by t. What we are going to do now, take the probability limit of this whole thing. So this is a constant, nothing happens. When we take the limit, what's going to happen here is that this goes to 0, see? Because of this hypothesis here. And this thing here, because we are in a linear regression framework, the probability limit, this is also 0. So what we have is that the second term goes to 0, the third term converges in probability to 0. Okay? So we have that the probability limit of beta reach equals to beta, the true parameter, when lambda diverges, but diverges at a slower rate than the sample size, and of course when we have like p less than t. We need that because otherwise these things here won't converge to anything reasonable. Okay? And we can also show what the distribution of the reach if square root t over t times lambda converges to a constant. So lambda does not diverge, okay? And t goes to infinity. So beta reach will be biased. This is the bias. but the de-biased estimator will converge to a Gaussian random variable. Okay, so we know pretty well what ridge is doing when we have low dimensions. Okay? It introduces a bias, but it decreases the mean squared error. Okay, so because it decreases the value, so there's an optimal value of lambda that makes the MSE goes down. Okay, so that's what I have to say in terms of low dimension properties of the ridge. All right, but what else ridge is doing? Ridge works because we augment it, but why this shrinkage is particularly interesting? So let's look at the singular value decomposition of the data matrix X. So our data matrix X can be decomposed as UDV, calligraphic U, D, calligraphic V transpose, where this U is a T by P orthogonal matrix such that U prime U is identity. Okay? D will be a diagonal matrix, a P times P diagonal matrix consisting of the singular values, these, which are the square root of the eigenvalues of X prime X. Okay? And V will be V1 to Vp, also a P times P orthogonal rotation matrix such that V prime V equals to identity and V prime also equal to identity. Okay? All these things I'm assuming here that P is less than T. A similar reasoning also holds for P larger than T. But instead of having P times P diagonal matrix, we are going to have a T times T, and here we are going to work with X, X prime, not X prime X. Okay? But the intuition is exactly the same. Okay? It can be shown that the beta ridge can be written this way. The calligraphic V, a diagonal matrix of the ratios between the singular values and the square singular values plus lambda times calligraphic U prime Y. Okay, looking at these expressions, say, no intuition at all, can be anything, I cannot interpret that. So what we are going to see in the subsequent slides is how to give an interpretation for this expression and what we can tell about ridge. So first thing, X prime X, remember the decomposition, the SVD decomposition of X, okay? So X prime X, we can write V d U prime U d V prime, which is equal to V d square V prime. So we can write beta hat ridge as V d square V prime plus lambda I inverse V d U prime Y, okay? So what we can do, we can take the identity here and make it V prime V. We can put V prime in evidence, so be V d square plus lambda V prime. Okay? This will be V prime inverse d square plus V lambda inverse V prime inverse V whatever comes after. And just simple algebra will give V d square plus lambda inverse d U prime U V Y d U prime Y, which exactly what we have in the expression in the blue rectangle. Okay? So in the derivation we use the fact, of course, that V inverse equals to V prime. Okay, again, okay, now this is the proof of the previous results. But what's the intuition? Why we are doing that? Why on earth we care about all these singular values? Well, as a consequence of the previous results, we know that we can write the prediction of the ridge, y ridge, it will be x beta ridge. But what's beta ridge? The expression that you have on the second line in the slide. But we can replace the beta ridge by the expression that we had from the previous slide, by this expression here. Okay? We can use this expression, let's plug in there. So what we have here is that the prediction of the ridge will be the sum of j equals to 1 up to p of uj, the elements of this matrix U, this ratio here, uj prime y. So it will be U, a diagonal matrix, where in the diagonal you have the ratios between the eigenvalues of x prime x plus lambda. Okay? Just for comparison, the OLS has no lambda. Lambda is 0. So this whole term here becomes equals to an identity. So the OLS is predictions just UU prime y whenever it's possible to run OLS. Okay? Right? So this is the second auxiliary result. So we wrote beta hat ridge in terms of the singular value decomposition of the data matrix. Okay. Then we wrote the ridge prediction in terms of the singular value decomposition. Okay. So far is a mathematical curiosity. But how this result can help us understanding what ridge is doing. Let's see in the second slide. Okay? And it's related to this last bullet point here. What it's doing. The larger DE is, okay, if this is really large, so this lambda as compared to lambda, what's going to happen here? Lambda is negligible compared to d squared. So dj squared plus lambda will be approximately equals to dj squared, which will be equal to 1. So whenever this will happen, whenever dj squared is much larger than lambda. But what's d? The square root of the eigenvalue. So d squared is the eigenvalue. So small singular values will be penalized the most in this ridge regression. So ridge is penalizing somehow the small singular values, the small eigenvalues. But again, how can I give an interpretation for that? So far, is a mathematical fact. Well, let's go back to the eigen decomposition of x prime x. X prime x is v d squared v prime, using the singular value decomposition. And the eigenvectors Vj, the elements of this matrix V, are called the principal directions of X. Okay? And I'm assuming that all the eigenvalues are ordered. Okay? Such the respective eigenvalues will be associated with the ordered eigenvalues. Okay? So we say that gamma j, that X Vj, that equals to Uj Dj, is the jth principal component of X. So what's a principal component? We are rotating the data matrix, and we are selecting this rotation in such a way that the first principal component is the one which explains most of the variance in the data. The second principal component explains the most remaining variance, so on and so forth. Okay? So ridge regression is projecting Y on the principal components with large dj compared to lambda. So OLS you are projecting on all the variables. Ridge, you rotate the variables and you project on all the principal components, but you give more weight to the principal components with the larger eigenvalues. So you take into account in the regression all the principal components, but with a weighting function that depends on the ratio between the eigenvalues and the penalty parameter lambda. Okay? And as I mentioned before, x prime x can be singular, but x prime x plus lambda I is not. And the reason is because this matrix depends on the coefficient that's different from 0. Okay? So that's what ridge is doing. It's projecting on the space of principal components, giving more weights, or penalizing less, let's put it that way. I think the most correct thing to say is that it penalizes less the principal directions, the principal with higher eigenvalues, the most important principal components. Okay? When x is orthogonal, then x prime x equals to identity. So we have some closed formulas. So ridge is related to OLS in a clear shrinkage way. So ridge is shrinking the OLS estimator. Okay? There is an optimal choice for lambda in closed form that depends on p sigma square and the sum of bj's, where sigma is the variance of the error. And when x is not orthonormal, we have to select lambda by data-driven process that we are going to see in the third block. Okay? So going back to ridge and principal component regression, remember that the principal components given by x vj. Okay? So what you usually do in principal component regression is that we compute the principal components of the data. We take the first k most important principal components, okay, and then we regress y on the k most important principal components. So we are projecting only on k principal components. So we're doing a kind of thresholding because we define a pre-specified threshold and where we're going to select just the first k principal components, and we regress y on the first k principal components, and we discard the rest. Okay? Ridge, we are projecting on all principal components, but we are going to shrink to 0 the coefficients associated with the less important principal components. So ridge can be seen as a smooth version of principal component regression. And that, for me, is one of the most beautiful properties of ridge regression. And it explains why it works also on forecasting. It's related to factor models that we are going to study later in this course, right? So this is a very, very nice property that I'll be willing to discuss more with you during our live meeting on Friday. And that's it for our second block. See you soon on our third block.